So, the topic I would like to talk about today is actually two of, I, I, I I think I can say it, two of the papers that are really the best, some of the best papers I've ever read. And those are StyleGAN and StyleGAN 2. So, there is a lot to be said about those models, and truly it will be quite hard to condense it so that we can fit the time this evening. But I think I can still get the gist out of it. The reason why I really wanted to talk about this and uh, rather sooner than later is because, as you may have heard, with GAN research, time flies. So if I had given this talk, I don't know, 2 or 6 months ago, 2 or 6 months in the future, sorry, it might already be irrelevant. And actually, those works are already respectively 1 and 2 years old, which is kind of considered old in that field. So I really wanted to present this before it gets totally obsolete. And at the moment, I believe it is not obsolete because AI is kind of there is this kind of idea in AI that in order to get an interpretable model from a model that is not interpretable, you have to make a compromise, right? And this is something we retrieved in the field of NLP with what Leo just told me. But what I would like to talk about today is like this tiny little light of hope that you can see sometimes in some paper. And I believe that with the field of image generation, and especially with GANs, we can see this tiny light of hope. This tiny light of hope that is the fact that actually reaching an interpretable solution is actually the best solution, maybe, that we could reach. And therefore, working on interpretability also means working on quality. So I would like to present those papers to you, and I hope that after that you will feel as I am, because I really feel that there is something there. So here are the two papers that I want to talk about. StyleGAN is called a style-based generator architecture for generative adversarial networks. And StyleGAN 2 is called Analyzing and Improving the Image Quality of StyleGAN. Now, you might notice that they are by the same authors who basically kept working on the same subject and improved it. They are working at NVIDIA. And what is very cool about their research is that all the code is widely available. And so it is very easy to reproduce. And a lot of people have actually done so to apply it to different fields. So before talking about StyleGAN per se, I would like to just go back very, very quickly on the basic groundworks to understand what I will be saying. So first, let's do the just-in-case slide. The just-in-case slide is to just put back into the mind of everyone what a generative adversarial is. But I would expect that all of you or most of you actually already know what it is. So let's just put the vocabulary back into everyone's head, because maybe you're not working with it every day. So a generative adversarial network, also called GAN, is when you train a generator to the task of generating some data. In most cases, it will be images. So in order to do that, you need a real database, which you call real because they are images taken in the wild. And then you will feed a random vector, which you call the latent vector, into the generator so that it generates an image. And then this image will be sent, as well as images from the real database, into another neural network, which is called the discriminator, whose task will be to determine whether these images are real, in the case of the real database, or generated when the image comes from the generator. And just like that, if you train this using the adversarial loss, which are actually two losses, one for the discriminator and one for the generator, this dynamic system of two neural networks can converge, sometimes, if you're lucky, towards a situation where the generator actually learned the distribution of the dataset. So now that we have just laid this down again, I would like to give two other reminders, and I'm sorry about all those reminders, but I do believe that they are important to understand actually how StyleGAN work. So this first one, it will be about the growing GANs. Growing GANs are basically a certain style of GANs where the generator and the discriminator grow with time over the time of the training. So, for example, you would have first something that converts the latent vector into a 4x4 image, and then the discriminator would try to predict if this 4x4 image is actually realistic. And since this 4x4 image does seem like a very, very realistic 4x4 face to me, well, in that case, it would say that, yeah, it is a correct face. And then after this 4x4 model has been correctly trained, we will add another layer that actually upsample this to 8x8. And the discriminator will also try to determine if 8x8 images generated by the generator are real or not. And just like that, improving and growing slowly, we can grow onto very high quality images that actually do look quite realistic. And now in 2021, we might seem that those very realistic images are not that impressive because it's been some time that growing GANs have been around. But actually, when the growing GANs paper was published, it was the first time that such incredibly high resolution images were generated with human faces that you might just be fooled by. Of course, this growing GANs architecture has been beaten many, many times since then. And we will see why when we get to the actual StyleGAN. But this is very important because this growing strategy has been reused by many works after that, even though nowadays it's no longer used. It has been the groundwork for a lot of advances in that field. Now, something else we want to talk about here is the problem of conditional generation. So conditional generation is basically when instead of predicting just the image, you want to predict the image knowing something about the image, anything. That could be the class, if the dataset contains several classes, or you could just give it a certain feature of the image, certain style, for example, and then the goal of the generator would be to generate an image that corresponds to this style or that corresponds to this particular feature. So the main thing we could wonder about is how do we get into the GAN structure this information about the feature that we want to bring into it, so that the generator knows what to basically create. And the first versions of this were actually very crude. Like you would just take this feature that you want to that you want the generator to have, and you would just add it as an additional input. And if this additional input is correctly used, well, then it would mean that the generator can produce an image that corresponds to the desired label. And it also means that the discriminator should, in theory, be able to retrieve the fact that it was indeed this particular label that was used. So a good way to do that, to ensure that, and to send a signal back to the generator to tell it that it was actually, yes, the correct label, is to just have the discriminator predict, in addition to whether it is real or generated, the label that was used in the beginning. So this structure is very rough because the main problem is basically that you treat this label that has a very specific semantic indication. It has a value, it brings information, and you mix it up with a totally random vector, which it is true. We want to make this latent vector carry meaning over time. And actually, we even want to be able to disentangle the latent space so that we can retrieve that meaning. But in the beginning, it doesn't have any meaning. So it is kind of strange to add this kind of very meaningful element to something that has no real meaning. And it didn't make it very easy for the generator and the discriminator to learn what was supposed to be done here. However, with time, we have seen many ideas in order to more smartly incorporate this label into the structure. And one of those has been using normalization layers. So you may have seen normalization layers before because they are quite common nowadays in a lot of different neural networks. A normalization layer usually looks like this. So you would have a certain neural layer, and then at the output of this neural layer, instead of feeding the output directly into the next neural layer, you would have a normalization step where first we would do this normalization function that I just call norm here, but that basically amounts to removing the mean and then divided by the standard deviation. That can be computed over either the instance itself or the channel itself or the batch, and then that would give you batch norm or instance norm or any kind of normalization method that you want. And there, usually after this normalization operation, you would multiply by alpha and add beta. And that's very interesting actually, because usually the way that we choose this alpha and this beta is we just set it as parameters of the network that should be trained over time. But it was quite some time ago. I believe it can be traced back to 2016, when some researchers had an idea that was very interesting. They said, instead of learning these alpha and beta parameters, maybe we should just take our desired labels and then linearly project them to some alphas and betas, which we can give to this normalization layer. And then we will have found another way to bring this information to the network. So we will no longer learn what alpha and beta are, but instead we will learn the linear projection from the desired labels to alphas and betas. And it was actually very interesting, because usually if you apply this to a normalization method that is applied to the whole channel, then you get a very spatial invariant way of changing the whole channel that comes out of your layer. And that's very interesting, because usually a feature that is a space invariant is in a way correlated to what we describe as style in an image. And indeed, the paper that first introduced this notion was trying to establish a way to learn style automatically. So that's where the style from StyleGAN comes, basically. But StyleGAN is not actually a conditional GAN. It's actually just a normal GAN. So what is it that we are sending into alpha and beta if it's not a desired label, if it's not a condition? Well, let's see that. For now, after a few minutes of presentations already, we are finally going to see what is StyleGAN. So StyleGAN is basically a GAN where the generator gets modified quite heavily. You see, when StyleGAN was published, the authors claimed that the discriminator had seen a lot of research, and also the training setup of the GAN had seen a lot of research. But actually, the architecture of the generator was usually very simple. And they found it kind of sad. So they wanted to give the generator a little bit of love. So let's see what they did. So this is a usual generator. In a usual generator, and more specifically a growing generator from the growing GANs, we would have the latent space. So the latent vector would be Z drawn into the latent space big Z, like that. And then this is the usual generator, where you would just apply some normalization and then some layers, and then upsample to go from 4x4 to 8x8, and then some layers again with some normalizations, and then upsample again to get to 16x16, etc. And you just stack that until you're done. And they said, okay, let's take this and change it completely. So basically, we are going from that random information, upsample modify, to now something that looks a little bit like this. So here, it actually kind of looks the same, right? We do have something as the input, and then this is also a normalization layer. This is also a normalization layer, convolution. So actually, this looks a lot like what we had here, but we do have a lot of arrows coming into that. So let's see what those do. First, you might see that here we actually have a constant, And here in my block representation of that model, you can see that actually the initial state is now learned. So that might come as a shock because it doesn't make a lot of sense to learn the initial state. If you don't have a random vector as your initialization of the network, how can you generate different elements? Well, that is because now that random information that we always had as the input of this stack of layers, we're going to have it on the side. And actually, we are going to bring it in using that trick that we just saw. So within those normalization layers, we are going to bring betas and alphas in order to rescale the normalized information. And that rescaled information will come from a neural network that will have transformed a latent variable. Okay, so what does it mean? Why do we do that to begin with, right? How can it work? The idea is that we will go from kind of the average face of the dataset, if we're talking about face. And then we will apply some styles to that face. So for example, is it the style of a man or a woman? Is it the style of someone who has long hair or short hair? Is it the style of someone who has gray eyes or blue eyes, etc., etc.? And actually, all those styles will be kind of a scale that would be applied to the state of the information vector that is going through the main stack here. And this would mean that at every single step, we would kind of change the statistics of the vector in order to scale it to a certain certain style scale, and then bring changes at this scale. So what this basically creates is it tells you what scale you should be at in order to make your modifications. But then, of course, this is still a lot less random than what we had before. So in order to change that, we can just take some noise and add it here and there. And that will be very important because it will avoid the network to kind of collapse to an average state. With this noise, you will be actually able to generate very fine details such as hair that can be at very different places, even though the person is the same, for example. So that is basically the StyleGAN architecture. It was a very, very big change for GANs because even though there had been ways before to bring in information like that, and even though it had also been possible before to actually start from a constant vector and bring this latent vector through those, it was the first time that all of this was put together with some additional noise and a mapping network F. We should talk about we should talk a little bit more about this mapping network F, I believe, because it is quite an important component. It might seem as it's not doing much, right? Because we start with a random thing, and then we process this random thing to give us something else that seems equally random, but that's actually what will be sent in our different normalization layers. But actually, they will actually they will actually claim that this first mapping network F is their main contribution, and I totally believe that, because by adding this mapping network F, they are able to change however they want the shape that this latent space has. If you send this latent space directly into the network, it constrains this latent space in order to make a good use of it. And it forces this latent space, that is a Gaussian latent space, to have to acquire certain properties so that the GAN can work properly. And these properties are sometimes very difficult to enforce, which leads to a lot of instability. However, if you first transform that space into a space that will be tailor-made so that they can handle those constraints, then you get something that might actually work a lot better. and especially that you could be able to tweak and to change so that it gets the properties you have, because now you are no longer restricted by this latent space that you generate using a Gaussian distribution. And that is one of the main selling points of their network. They want StyleGAN to be interpretable, to have very nice properties, and if possible, all the while beating all the previous state of the art in terms of quality. They want StyleGAN to be able to be extremely nice to use, to be, if possible, easy to inverse, to be, if possible, interpretable. And this is why they designed two metrics. I unfortunately don't have the time to cover both of those two metrics, but let's talk about one of them, which they call the perceptual path length. So what is the perceptual path length? When it's a way kind of to check if the properties of this latent space, this secondary latent space, W, is actually has a good topology with respect to this one. So what do I mean by that? Because I know that my use of the mathematical terms here is not very rigorous. So what do I mean by that? Basically, they want that when you do a small step in a certain direction in this space, it amounts to a small step in the semantic space of the images. So if you take your images that go out of the GAN and you send them into VGG or something, and you get some semantic information, they want that when you interpolate between 2 points in this space, well, the speed of your interpolation conditions the speed of interpolation within the image space. And especially, they don't want that some features suddenly appear from the void, even though those features are completely absent from from the start or the end of the interpolation. For example, if you go from the picture of a woman to a picture of another woman, you don't want in the middle to have the picture of a man. That doesn't make a lot of sense. It translates, it means in a way that our space here is quite entangled, and we will not be able to derive nice properties and nice interpretations from it. So if this perceptual path length is low, they claim that it would mean that their space here has very nice properties that can be used more easily. Now, that was StyleGAN 1. Now, let's see a little bit more what kind of results they got. Because I don't know if I've said it before, but this is actually also, this actually made state-of-the-art results in terms of quality. So let's see. These are some results from StyleGAN 1. So quite stunning, two very stunning pictures, if you ask me. And by the time this was published, this had no equivalent. However, if you look closely, you might see that there are some problems here. And maybe it will be hard to distinguish here if you don't know what to look for. But if you look here and here, you have actually some very strong artifacts that look very strange, especially given the fact that the rest of the image, except for the background, which is as usual for GANs, just a jumbled mess, these ones kind of strike as odd, especially because they are located around the same place for both images, which is a little bit strange. And then there are also other kind of mistakes that can appear. Let me show you another example to emphasize on this. So this was another kind of example that could be generated. And again, this might not strike as strange at first glance, but actually when you know what to look for, you can never see this picture again and not laugh. Because if you look at the teeth here, you can see very quickly that this is not normal, right? This doesn't work like that. So basically, what sparked the interest to create StyleGAN 2 were these two very strange behaviors, where things that should in theory be very easily detected by the discriminator kind of strangely went unseen and made their way to the final version of the generator. So let's see how they solved that. So the main thing that is going on here was this strange artifact in the form of a dot somewhere in the image. And actually, they trained over several data sets, and they saw that this artifact was always present, which was a little bit strange. So they deduced very rightly that there was a flaw inside of their architecture that forced the network to systematically create this kind of dot if it wanted to converge. And they were able to find this problem. Actually, if we look at this more detailed representation, so basically this is the same representation as before, except that we have split the normalization layer into the part that actually normalizes and the part that modularize the result with the elements that come from there. So multiplied by alpha plus beta. And then here, the convolution has been split between the actual convolution and the application of the bias, right? And from this, what we actually notice is that before every style block, we need to normalize so that the normalized information can actually be put to the style scale that I was talking about before. But that means that all statistical information from before is lost in between two style blocks. And it is very hard to retrieve. So they had the hypothesis that maybe the only way for the network to actually send some statistical information from a certain part to another part later down the line would be to create an extremely high intensity part somewhere in the activation maps that would carry such a strong signal that it would survive the normalization, basically. And they have quite strong experimental evidence to prove that. And especially when they remove this normalization part, well, it will all work out very well. But you might wonder, how can we even remove this normalization part? Because then our modulation here doesn't mean anything anymore. Well, the way they chose is that basically they decided that if you can apply this modulation to the incoming input, it could actually be equivalent to apply it to the weights of this convolutional layer, and that's what they did. So if we have a look at their new architecture that they use here, the constant that is here at the beginning of the network actually only goes through convolutions and then gets added with the biases and the noise. And that's all that happens because everything else happens inside of the weights of the convolution. They actually first get modulated by alpha and beta here, and then this demod operation kind of replicates what we would expect on average to have by this operation. I don't think I can go into details right now, but if you would like to come back on that, I would be happy to do so after further questions. Now, this was one thing, the weight modulation. They also added this perceptual path length regularization, where they basically said, hey, we found a very nice metric, the perceptual path length, but what if we could use it to actually regularize our network and make it so that we enforce this very nice property into our latent space? We can come back on the specific the specific formulation that they used for that later as well, but that was basically their idea there, and it worked quite well. And finally, what they wanted to change is this growing architecture. I mentioned that the growing architecture over time had been kind of put away. And that is because it actually forces the neural network to do this realistic 4x4 image and then this realistic 8x8 image, etc., while actually we don't care if those scales are realistic. They just need to convey the correct information to what's next. Right, and so it's not actually exactly the same goal, and they could infer from that this was actually what generated these very strange teeth errors. And indeed, when they went away from that growing architecture and replaced that with an architecture that used residual connections. So here, for example, if you have a look at the discriminator, we have this residual pipeline down the middle here. And then at each stage, the features coming from the previous stage would be processed by something that would upsample them as usual using deconvolution operations. And that would then get added with the same ones that would just go through an upsampling operation like bilinear operation or something like that. And so this kind of residual pipeline like that, well, if you think about it, it helps by allowing the network to train all at once and not stage after stage as was done in the growing GANs paradigm. However, it still allows the network, if it is useful, to first train the first networks, the first layers, sorry, and then progress naturally towards the biggest layers, because the gradient at the first has just there is just this highway of gradient down the middle here that doesn't need to go through those layers at the same time. And they told themselves, actually, maybe we will recover the properties of the growing GANs without even enforcing this growing property. So they tried to measure that. And to measure that, they just tried to measure the impact, the importance of every scale as the training goes on. And what they saw indeed was that in the very early stages of the training, the very low scale has a lot of impact. And then as the training progresses, as if we had this growing GANs method, well, the low scale parts here gradually become less and less important, while those parts here become more and more important. So in a way, without even enforcing it, this growing GAN property now naturally arises just from the fact that we allow it to arise if it is relevant. And here, since it is relevant, it happens. That's part of the beauty that I was mentioning about these architectures, right? You just set the stage right for things to happen if things go well, and nice properties arise from this just from this setup. Now let's have a look at some numbers very quick, just to set things straight for those who like numbers, because I know that there are a lot of people who really like numbers. So if we have a look at those two data sets here, Celiba HQ, which is the classical one, and FFHQ, which is basically the a data set that they introduced in the StyleGAN paper, we can see that indeed in this how do you say that? When they removed all of their contributions and gradually added them back, you can really see that indeed all of their contributions, some of those I haven't covered, by the way, but yeah, those are some very dense papers, very difficult to cover in a single session. The FID score goes lower. And here you have the path length metric experiments, which really show that going from a traditional generator to a style-based generator with this W additional latent space really improves this kind of metric. There is this other metric that I was talking about before, where the improvement is even more impressive. And then I believe this here is StyleGAN 2. Yeah, it is StyleGAN 2 because now the baseline is StyleGAN, while it was the growing GANs here. So StyleGAN is now the baseline, and there was a huge improvement, nearly a 100% improvement in terms of FID here, going from the sample from 4 to half that amount. And the last thing I wanted to talk about is this graph here, which is also actually very interesting because this shows the capacity to inverse the generator. The inversion of the generator is actually a very important topic because it allows you to find the latent vector that generated a certain image. And this is all the more important that nowadays, because of all those deep fakes that might appear from those very, very powerful generators, it becomes very important to be able to trace those fakes back to the generator that produced them. And here you can see what happens when you try to invert the generator and you compare the statistics of an inverted real sample and an inverted generated sample. Here you can see that for the StyleGAN baseline, those two statistics look the same. So it is very, very difficult to differentiate a fake sample from a real sample. And here for StyleGAN 2, we notice something very strange. Even though StyleGAN 2 has an FID that's even better than before, so the quality is better and it's even more indistinguishable from a real sample, even though we have made progress in that direction, the generator is more easily inverted, which means that it is more simple than before to distinguish generated data from real data if we have access to the model, which is the case because all the models were released. So what this shows is really what I was talking about in the beginning. You want something with good properties and you expect to have to do some kind of trade-off with quality to reach those good properties. But what if actually there was a way to reach those properties just because the world is well made and what actually works also works while having nice properties? Just like when we created mathematical models to describe what we thought was logic, we kind of realized that those equations also applied to the real world. That is the kind of beauty that I like to see in GANs, and this is why I say that those papers, even though they are not perfect by a long shot, if you read them, you will see that some experiments are a little bit shaky, some claims are not that well justified. Even though all of this is true, this is still what I would really call a light of hope. Okay, thank you everyone for your attention. If you want to go further, I would definitely encourage you to check out those two papers over here. They are very interesting if you want to really learn more about this topic, and do read the original articles that I was talking about. As I mentioned, I really couldn't cover it all. Okay, thank you very much. And if you do have any questions, I would be very happy to answer them.